Hello everyone. Today we're going to see some limit problems that you have seen before, but since you have the final exam in 1 week or maybe a little bit more, so I want to give you some quick review of the things. One of the most important limit techniques that we have used is called the squeeze theorem, and I'm going to show you some problems from squeeze theorem. Okay, so the squeeze theorem. I've never used this board before, so everything is like an experiment. The squeeze theorem. Let me just remind you the statement. Let f, g, and h be three functions such that f of x is, I'm going to change my notation a little bit. Let's make it g of x is less or equals to f of x is less or equals to h of x for all x near c. C is some point except possibly at c. So let me explain you what it means. It means that this function f, it is between g and h. It's kind of sandwiched between those two things. That's why this theorem also has a name called sandwich theorem. And x is near c, that means there is an interval containing c, and these inequalities are satisfied by every number from that interval except possibly c. And you should know this, why it's we are allowing this thing that except possibly at c, because when you consider limit, it doesn't matter what happens exactly at that point. We can completely ignore that point. All right, so if that is that happens, and then we need one extra thing. If limit of g and limit of h exists at c, they exist, and they are equal. Now that part is very important. Then now what happens, you see, f is trapped between g and h, and both g and h, they have limit and they are approaching one fixed value. Okay, then this function f also has limit at c, and it equals to this common limit of the other functions. Okay, so now that's the statement, and we're going to use that as statement to solve some problems where we cannot find limits using conventional tools. One of the classic examples of that is this. Let's evaluate this limit of this function x squared sine 1 over x as x approaches 0. Now, one of the biggest problems of this thing is sine 1 over x. That function does not have a limit at 0. It is an oscillating function. It goes, captures all the values from -1 to 1. That's a really bad kind of way not to have a limit. X squared has a limit, but the thing is, this is a very common mistake to use the product rule of limit, that you take limit of x squared as x approaches 0, which is 0, and then you take limit of sine 1 over x as x approaches 0, which is whatever, and then you say, since this is 0, 0 times anything is 0, and therefore this is 0, right? But there is a mistake. What is the mistake? When you say 0 times anything, there should be something, and that thing should be a number, right? But sine 1 over x as x approaches 0, that thing is not a number. There is not a specific number. That limit doesn't exist. So there is nothing there that you are going to multiply with 0. So that technique will fail. Okay, so we need to actually trap this function between two other functions like g and h, and then we'll see if we can get those two functions have the same limit, and then we're going to use the squeeze theorem to find this. Okay, so we saw the statement of the squeeze theorem, and now let me just work out an example. So example, evaluate this limit of x squared sine 1 over x. Okay, and as I told you before, the problem here, oh sorry, x approaches 0. Yeah, we need to get there. So wrong way. So let me write the wrong way of solving this. So this is a very common mistake, so I want to write it down and then I want to show you. So what people do is they use product rule here. So they consider this as one factor, that as another factor. So they get this product rule wrong and write this thing. Now since this is 0, they say 0 times anything or nothing is 0. But that's not true. You need to have some number, right? And I want to cross this out, and I just want to say never do this thing. This is awful. Okay, that's completely wrong. So don't do that. Product rule does not work here, and that's why we need to go to the squeeze theorem. So how to solve this thing? And as you have noticed from the squeeze theorem, you need to actually trap this function between two other functions. And we need to build those two functions that actually captures this function x squared sine 1 over x in between. Okay, so how to actually get there? So that let's call this function f of x equals to x squared times sine 1 over x. And the key idea here is this is one of one of the important properties of sine. I mean, not too important, but this is a knowledge of sine theta, that we know that sine and also cosine of anything is always in between -1 and 1. If you look at its graph, it never actually goes above 1 or below -1. So that means if my angle is 1 over x, then the sine of 1 over x is also trapped between -1 and 1. So that's for sure. Alright, so the good thing here is I have something on the left and something on the right. So we are heading towards that, right? But still we lack something, right? We need this guy x squared. So we need to have x squared there. And how can you get that? Of course we need to multiply, right? But if you have inequalities or equations, you cannot just multiply in one side. You need to keep multiplying in each term, right? So I need to multiply x squared in all three terms. So this is going to be negative x squared. This is going to be x squared sine 1 over x. And then this is going to be, oh god, I'm going to actually postpone this thing for a while. Okay. Yeah, I killed the suspense. Anyway, so what should be my inequality here? Inequality is tricky. If you multiply by numbers, inequalities can change. So here, should my inequality be the same or should it flip? It should remain the same. Why? Because x squared, that's a non-negative number, right? It's always positive, and when x is 0, it's 0. But 0 will make everything 0, they will be equal, so that's fine. So this inequality signs will remain the same, and so does the other one, okay? And you need to justify this thing, since x squared is greater or equal to 0 for all x. Okay, so very good. So now notice that if I just want to write down this as we have stated squeeze here, I mean, notice this is my function f, this is g, and that is h, right? And now what we need to actually check the limit of this function and that function at 0, okay? Now, since limit of this function is what? Negative x squared as x approaches 0. What is that limit? It's a polynomial, right? You can just plug in. So this is negative 0, which is just 0. But what is limit of x squared, this function on the right side? As x approaches 0. That is also 0, right? Okay. Now this line actually, it seems one line, but it says actually three things. First it says this function on the left, it has a limit. And then it says the function on the right, it also has a limit. And finally it says those two limits agree, they are same. Okay, so in one line we actually capture three information, and that means all the hypotheses of squeeze theorem are satisfied. Okay, by squeeze theorem, then squeeze theorem, we have our function has limit 0 at 0. Okay, so limit of x squared sine 1 over x as x approaches 0 is 0. Okay, and notice those two answers are same, but this is a very wrong way of getting right answer. That's not good. Okay, it's better to get wrong answer but to take few right steps, but to take wrong step from the beginning and get the final answer right, that has no meaning, that's useless. You are very fortunate to get this limit here, but in many cases you will not. Okay, so this is a very simple example of a function that whose limit you cannot figure out without a squeeze theorem, but this is also very illuminating. We are going to see one or two more problems like this, but right now I need to take a break. Alright, so we're going to do one more problem and then we'll end this video. So this problem is find this limit, evaluate this limit of a square root of x minus 1, and then this will be let's say 3 to the power, okay, so we have sine, let's make it cosine. Okay. And then let's make it even crazier, pi over x minus 1. And x should approach 1 from the right. Because the domain of this function x minus 1 is like all numbers which are bigger or equal to 1, right? Now, what are some issues? First of all, this function, square root of x minus 1, that we can take actually limit, because it's a square function which is continuous, and then x minus 1, that's a polynomial, so it's a composition of 2, and this limit is 0, and then you can take square root of that because it's continuous, that is 0. You can do that. 3 to something, that's also continuous, but the problem here is we have cosine of pi over x minus 1, so there is like another composition with 1 over x minus 1. Now that's the heart of the problem. Okay, so we have this rational function. This is the problem, and it's not continuous at 1. It's not defined, so it's not continuous. So we cannot actually directly plug in 1 there to get the limit. Okay? In other words, what I'm saying is this limit is 0, and that limit is whatever exists or does not exist. Therefore, this is 0 times that equals to 0. If you go around that direction, then you are totally wrong. That's what I want to say. Okay. Now, how to solve this problem? So, solution. Once again, if you have cosine of sine, the great thing is you can start with that bound from trig. So we have cosine of anything is okay, so let's just keep it. Cosine of anything is between -1 and 1. Okay, and the thing we have, the input is pi over x minus 1, so that's some angle. So if you take that angle under cosine, then that's also going to be between -1 and 1, that's for sure. Okay, now we need to gradually build up this function, right? And what do we need? This is 3 raised to the power cosine. It's not 3 times cosine. You don't multiply. You have to take powers. So I need to take powers of 3 in all 3 steps. So this guy is going to be 3 raised to the power negative 1. This guy is going to be 3 to the power cosine of pi over x minus 1, and this guy is going to be 3. And now there is a big question. So what will happen to my inequalities? Will it remain the same or will it change? Like this one or that one? That question, the answer to that question is this: the inequality signs will remain the same, but you need to justify that. Why is it the same? Since 3 to the x is an increasing function. What it means is this thing. So how does the graph look of 3 to the x? So let's say this is x-axis, this is y-axis. So 3 to the 0 is 1, 3 to the 1 is 3, and 3 to the negative 1 is 1/3, so it's like this. And so that's the graph of 3 to the x. Now, if you plug in bigger values, so okay, where is negative 1? This is negative 1, and this is positive 1, right? So, negative 1 is here, positive 1 is here, cosine of that number is somewhere in between, okay? So let's say it's somewhere here. That's my cosine pi over x minus 1. And therefore, you see, when you raise this to the power, 3 to the negative 1 is here, right? Which is on your y-axis, it is like this. 3 to the power cosine pi over x minus 1, that will be this point. So in the y-axis, that's the point there. And then 3 to the 1 is 3, it's there, right? So you notice this is, let me write this way, I don't know how this will look at the end. So this guy is 3 to the negative 1, that guy is 3 to the 1, and this guy here, this is, okay, not a good idea maybe. So this guy is 3 to the power cosine pi over x minus 1. Okay. So that shows why this inequality signs will be preserved. Okay. We needed that, that's very important. Alright, so what do you need? We get all this part. The only thing that is missing is the square root of x minus 1. Okay? Now, a square root function, that's also positive. So this is the square root of x minus 1. There is 1. And it goes like this. It's positive. It's above x-axis, right? Or 0. So we need to multiply each term by this square root of x minus 1. And then this is going to be, by the way, 3 to the negative 1 is what? 1/3, right? And then we need to multiply this, the square root of x minus 1, okay? And then this is going to be our function, square root of x minus 1, 3 to the power cosine pi over x minus 1. And finally, this is going to be 3 times the square root of x minus 1. Okay? Does it make sense? And why should the inequality signs will be preserved? Since you need to justify every time you have some inequality, since the square root of x minus 1 is positive or 0. Okay? So what we have done here, we have trapped our function in between two other functions whose limits are easy to calculate. Okay? Now, what is the limit of this leftmost function? 1/3 the square root of x minus 1 as x approaches 1 from the right. Square root is a continuous function and x minus 1 is a polynomial, so you can just plug in a 1 and evaluate that. So this is the square root of 1 minus 1, which is square root of 0, which is 0. 0 times 1/3, that is 0, right? And what about the rightmost function? That is 3 times the square root of x minus 1, and similarly you just plug in 1 and that becomes 0, and we get this, right? So we get 3 things. The leftmost function has a limit at 1 from the right. Rightmost function also has a limit there, and those two limits are equal. Therefore, by squeeze theorem, get our original function to have limit 0 as x approaches 1 from the right. This as x approaches 1 from the right is 0. That's how we solve this problem. Yeah, I hope it helps, and I hope you enjoyed the video. Make sure you learn this thing, because for you guys, I have left using my left hand. I've written using my left hand. Is it true? No, that's cheating. Anyway, yeah, see you next time.